Polarity is a really interesting topic in chemistry because it explains a lot about why molecules interact with each other in the ways that they do. It can also be a little bit of a daunting topic because we're going to have to learn how to consider the polarity of bonds and then the polarity of entire molecules. Fortunately, you probably already have a basic understanding of polarity even if you've never heard that term before. One of the reasons why is that the Earth is an example of a system that has polarity. You probably already know that the Earth has a northern hemisphere and a southern hemisphere, or at the very least, a North Pole and a South Pole. This is a system that has polarity. That's where we get the term pole or polarity. It has a north end and a south end. Now, another example of a system that has a north end and a south end is a magnet. We think of the north end of a magnet and the south end of a magnet of being opposite from each other. So if you've ever played around with a refrigerator magnet, you know that one side of the magnet will attract the refrigerator, while the other side will be repelled from the refrigerator. That, again, is a system that has polarity, a north end and a south end. So what does this have to do with molecules? Well, many molecules are actually polar systems in and of themselves. And the reason that that happens starts with chemical bonds. A chemical bond between two different atoms can actually be a polar system in and of itself. So it can have a north end and a south end. Although in chemistry we won't talk about having a north end and a south end, we'll talk about having a positive end and a negative end. The reason that a chemical bond can have a positive and negative end is that we already know that bond is made of electrons. Electrons are negatively charged, so when we end up with more electrons on one side of the bond than the other, that side of the bond becomes more negative, and thus we have a polar system. So polarity in bonds, and ultimately, as we'll see, polarity in molecules, occurs when we have electrons that are unevenly distributed. Let's look at the different types of bonds that come about when electrons are either gained, lost, or shared inside of a chemical bond. If we think about a chemical bond as just being the line between two atoms, we know that that's an okay way to draw it on paper, but in reality there's really more of a charge cloud that surrounds that bond. Now, if this charge cloud, which we know is comprised of electrons, is actually distributed evenly between the two atoms, that's what we'll call a nonpolar covalent bond. Again, a covalent bond just means the electrons are shared, and nonpolar means the electrons are spending an equal amount of their time in all areas of that bond. Or at the very least, they're not more on the left side or the right side. They're somewhere in the middle. That's a nonpolar covalent bond, but as we'll see, we can also have a polar covalent bond. Polar covalent bonds occur when your bond does have electrons spending more time on one side of the bond than the other. When the electrons are more likely to be found near one atom, we call that a polar covalent bond. So nonpolar bonds have evenly distributed electrons. Polar covalent bonds have electrons closer to one atom. And what's interesting about this is if you actually have a bond where the electrons are so unevenly distributed that they spend all their time around one atom, well, that type of bond, if you think about it, means the electrons have essentially transferred to one atom. Or in other words, you have an ion. You have an atom that's gained electrons and an atom that's lost electrons. And in that case, we don't have a covalent bond at all. We have an ionic bond between two different ions. Let's talk more about covalent bonds and polar covalent bonds in particular. Again, a polar covalent bond is simply a bond where the electrons are shared between the atoms, but they're shared unevenly. Now, why would two atoms share electrons unevenly? The answer is that some atoms do a better job of attracting electrons than others do. In this example, we can see that the electrons are spending most of their time near the atom on the right. That means the atom on the right probably had a better ability to attract electrons. A better ability to attract electrons is called electronegativity. We would say that the atom on the right has high electronegativity. The larger the electronegativity, the larger the attraction of that atom and its electrons. So in this polar covalent bond, the atom on the right has a high electronegativity, so it's attracting the electrons better than the atom on the left. Electronegativity values are something that you can predict following a basic trend on the periodic table or you can look them up. If you look at the values on the periodic table, most periodic tables that have only basic information won't have these values, but many more complex versions of the periodic table will include this information. Here's a chart that shows electronegativity values for many of the elements on the periodic table. The transition metals have been left out of the middle to conserve space. Notice that the largest numbers, or the greatest electronegativity, occurs in the upper right-hand side of the periodic table, near elements like fluorine, oxygen, chlorine, nitrogen, and so on. These elements are capable of attracting electrons better than most of the other atoms on the periodic table. The reason is they're fairly small atoms and they have a fairly large number of protons compared to the elements in the same period on the left side of the periodic table. So while fluorine and lithium are both in period 2, fluorine would like to attract electrons. It has a high electron affinity, while lithium would prefer to lose electrons to become more energetically stable. So fluorine is the most electronegative element on the periodic table, and from there it decreases all the way down to the lower left hand, where the elements are not very electronegative. To use this information in a chemical bond, again, you can follow the general trend, or if you have this chart, you can use it to refer to. If we consider a covalent bond between atoms like carbon and fluorine, here's a covalent single bond between carbon and fluorine, and if I wanted to determine where the electrons in this bond are spending their time, or in other words, where they're most likely to be found, I simply need to look at the electronegativities. Fluorine has an electronegativity of 4.0, while carbon has an electronegativity of 2.5. Because fluorine has the larger number, it will do a better job of attracting the electrons. One way we can indicate this is by using a delta negative and a delta positive sign to show where the electrons are. If fluorine has the higher electronegativity of these two atoms, it will attract the electrons more efficiently. And one way to show that is by writing a delta, which looks a little bit like an S that's fallen over, and to write a negative. This essentially means that there's a slightly negative charge on that fluorine. It's not completely negative, it's not an anion, but it's slightly negative compared to the rest of the bond. Carbon, on the other hand, has a slightly positive charge because it's not as strong at attracting electrons as fluorine is. We can do this for any covalent bond, and in fact we can do this for any bond that we want because the difference in electronegativities between these two elements can actually help us classify the bonds. When you look at the electronegativity difference between fluorine and carbon, since fluorine's a 4.0 and carbon's a 2.5, that's a difference of 1.5. 1.5 tells me that this is a polar covalent bond. And that's because there's a breakdown in electronegativity differences that's often used to define the different types of bonds. If we find two atoms that are close together on the periodic table, for instance, elements like carbon and hydrogen, if I were to connect carbon and hydrogen in a bond, in a covalent bond, and then look at their electronegativity differences, we'd see that carbon is a 2.5 while hydrogen is a 2.1. That's a fairly small difference in electronegativity. So any difference that's 0.5 or less, we would call a nonpolar covalent bond. And because this bond is nonpolar, I won't use the delta negative and delta positive symbols on it. With the carbon-fluorine bond, we determined that the difference is 1.5, so that is a polar covalent bond. So I will use the delta minus and delta plus symbols on the bond. If you go above 2.0, you're back in the situation where the electrons are so unevenly shared that they've essentially just been gained by one atom and lost by the other. And that happens in ionic bonds. So if you were to see sodium and chlorine drawn next to each other, it's pretty unlikely you would see a bond drawn between them because the chlorine has a 3.0 for its electronegativity while the sodium has a 0.9. That's a difference of 2.1, so it's an ionic bond rather than covalent. Remember that when drawing these bonds, if you determine a bond is polar covalent, you can use the delta plus and delta minus symbols to indicate where the electrons are spending their time in a bond. Now that we understand polarity in covalent bonds, meaning where are the electrons spending most of their time, we can consider molecular polarity. And the only reason that this gets a little more complex is that the molecules that we look at usually have 1, 2, or 3 or 4 or maybe even more bonds. A molecule can truly have many different bonds. And molecular polarity is really a result of looking at all of the bond polarities. Depending on its bonds, a molecule can be classified as a polar molecule or a nonpolar molecule. And just like we saw with chemical bonds, as well as a magnet, as well as the Earth, again, this is just indicating whether there is a north side and a south side, or a positive side and a negative side to the molecule. With molecules, even though there can be many bonds to consider, a molecule is considered to be polar when it has a positive side and a negative side, or a positive pole and a negative pole. And to determine that, we just need to look at each individual bond. Let's look at a couple different examples. Let's start with the example of carbon dioxide. We did the Lewis structure of carbon dioxide earlier, and if you want, you can pull that out or take a second, pause the video, and do the Lewis structure for carbon dioxide now. Okay, so I'm going to put the Lewis structure for carbon dioxide up. Here's the Lewis structure for carbon dioxide as we drew it earlier. When I look at this molecule and I want to consider its polarity, I'm going to look at each bond individually first. Let's start with the carbon-oxygen double bond on the left. As I look at this bond, I can compare it to my electronegativity chart, and I'll see that carbon has an electronegativity of 2.5, while oxygen has an electronegativity of 3.5. That's a difference of 1, which means this is a polar covalent bond. Since it's a polar covalent bond, I'm going to mark where the electrons are. Oxygen is more electronegative, so it will be slightly negative, and carbon is more positive. So carbon, it gets a delta plus sign, while oxygen gets a delta minus sign. Another way to do this, if you don't have an electronegativity chart in front of you, is just think which of these two elements is closer to fluorine on the periodic table. Oxygen is closer to fluorine, so it's going to be the negative sign. Now let's look at the carbon-oxygen double bond on the right. Not surprisingly, because this is another carbon-oxygen double bond, it will be polar covalent, and when I look at it, I'll expect that the carbon is the positive part and the oxygen is the negative part. So I mark that out on this example. Now, I've just determined the polarity of each individual bond. Now I need to evaluate the polarity of the entire molecule. One way to think about this is to imagine where are the electrons in this molecule. Well, on the left side of the molecule, in that carbon-oxygen double bond, the electrons are spending most of their time near the oxygen because it has the higher electronegativity. But on the right side of the molecule, the opposite is happening. The oxygen are pulling the electrons to the right because the oxygen is electronegative there. So when you look at this, it's impossible for me to say there's a north pole and a south pole, or a positive end and a negative end of this molecule, because I see that the molecule is slightly positive towards the middle and slightly negative on the outsides. That doesn't really count as a north pole and a south pole because I can't draw one line that represents positive and negative. So this is what we'll call a nonpolar molecule. There's not one positive end and one negative end. One trick that you might try if you have trouble understanding this is to try to answer this question. Can I use one word to describe where the electrons are in this molecule? That one word would have to be a word like left, right, up, down, front, or back. In other words, one of the three dimensions. I can't say the electrons are all on the left or the right because they're distributed to both places. And by the way, it doesn't count if you say they're in the outside versus the inside. That doesn't count here. So because I can't say all the electrons are moving to the left or all the electrons are moving to the right, I'm going to classify this as a nonpolar molecule. Let's look at another example. My next example is going to be nitrogen trifluoride, NF3. We haven't done this one before, so if you want, pause the video, take a couple minutes, and see if you can do the Lewis structure for nitrogen trifluoride, NF3. Okay, I'm going to put up the Lewis structure for NF3, and you'll notice when I do this that I have oriented the Lewis structure to have the correct molecular geometry. That often is very important when determining polarity. Nitrogen trifluoride has 3 fluorine atoms that are attached to the nitrogen, and there's also an electron pair on the nitrogen. Because of that electron pair, the entire molecule has the shape that we would classify through VSEPR theory as pyramidal. So notice I've tried to orient this molecule to look like a pyramid. That's important because often molecular polarity has to be considered in 3 dimensions. If you made this molecule flat, like trigonal planar, it wouldn't actually give you the same answer. So I have NF3, it has pyramidal geometry. Now let's look at each individual bond to see where the electrons are. I'm going to start with this nitrogen-fluorine single bond on the left. When I go to look at electronegativity values on a chart, or when I just remember the general trend on the periodic table, I know that fluorine is more electronegative than nitrogen, and I know that they're far enough apart on the chart that I would classify them as polar covalent. So I'm going to put a slightly negative sign near the fluorine and a slightly positive sign near the nitrogen. Now I'll move on to my next bond. Let's consider this nitrogen-fluorine bond in the middle. Again, same bond, so not surprisingly, I'm going to consider the fluorine to be negative while the nitrogen is still positive. And when I move to the third nitrogen-fluorine bond, I'll draw the same conclusion. In 3 dimensions, when you consider this, this means that the electrons are moving towards the fluorine in each case. The electrons are spending most of their time near the fluorine, or if you were to look for the electrons, you'd have the best chance of finding them near the fluorines. If you think about this in 3 dimensions, this is as if you have a pyramid and all the electrons are towards the bottom of the pyramid. Now remember our test for polar or nonpolar. Can you describe in one simple word where the electrons are? Well, I can't say left or right because they're going in both directions, but I can say they're not towards the top, they're towards the bottom. Or in other words, I could draw one line, one pole, that shows where the electrons are going. Because I can describe where the electrons are in one simple directional word, in this case, towards the bottom, I would call this a polar molecule. In other words, it has a north pole and a south pole, or a positive end and a negative end. On a polar molecule, we often show this information using what's called a dipole or a vector arrow. Your book just calls it an arrow. The arrow points in the direction where the electrons are going, and it's one arrow for the whole molecule that tries to represent all 3 dimensions. That's why it actually is called a vector arrow as opposed to just an arrow. So to draw a vector arrow here, take a second and look at where the electrons are. They're not towards the top of the molecule, they're towards the bottom. So if you could imagine this in 3 dimensions, I need to draw an arrow that goes straight down through the bottom of the pyramid. That's my vector arrow, or in other words, my dipole, 2 poles, dipole. By convention, we usually draw a cross around the top of the arrow to indicate that this is where the positive side of the molecule is, and we understand that the arrow points towards the negative side of the molecule. So the molecule on our right, NF3, is a polar molecule because the electrons are spending most of their time, or are most likely to be found, towards the bottom of this molecule. The carbon dioxide on the left is not a polar molecule. It's a nonpolar molecule because the electrons spend time both on the left and the right side of the molecule. In other words, they're distributed throughout the molecule. This is molecular polarity, and it is a challenging topic because there's a lot to consider, including all of the stuff we've been studying in Chapter 5. So let's summarize how to really look at these, so when you go to determine polarity on your own, you'll have a game plan. If you're trying to figure out if a molecule is nonpolar or polar, and you have to do it from scratch, meaning someone just gives you a chemical formula and asks you to tell them whether it's polar or nonpolar, generally, here's the best way to do it. The first step is to draw a correct Lewis structure. That means all of the bonds and electrons have to be drawn in so that we can determine the second step, which is the molecular geometry. So we saw before, it's important that if it's pyramidal geometry, we know that. Because if you go back to the last example and you had made that a flat triangle or planar triangular, you would have arrived at a different conclusion. So second step is determine the shape, visualize that shape in all three dimensions, and then identify the polarity of each individual bond on that shape. In carbon dioxide, we had 2 bonds to work with. In NF3, we had 3 bonds to work with. We determine the polarity of all the bonds, whether they're nonpolar or polar, and then, and only then, is it okay to try to figure out if the entire molecule is polar or nonpolar. So it can be quite a few series of steps, but it's important to work each one in order so that you can come to the correct conclusion. And if this seems like an awful lot of information just to figure out if something has a North Pole or South Pole, I can tell you from experience, it's really not. The fact is, behind this polar-nonpolar concept is the answer to everything, including why does water boil at a higher temperature than acetone? Why does Teflon not stick to things? All of that has to do with the forces between different molecules, and those forces come from determining whether a molecule is polar or nonpolar.